Alright, so now we collected the optical data and orientation. Now I'm going to set up a single crystal diffraction experiment. I'm going to solve the structure of this crystal and its orientation again, just for kicks. So yeah, I have Apex 3 opened up here on this diffractometer. It's really old. The detector's a little bit newer, but still really old. It's an Apex 1. This whole setup is a model from about 1994, so pretty old, but it still works. So this is a BISP. Okay, so now I'm entering in the formula, or rough formula. It doesn't have to be exact, but I have to put this down where it says formula, because I always do that. The compound is scolecite. The shape, I'd say it's prismatic. If it's equant, you can use that. If it's tabular, if it's platy, just enter in this other information, and I'll get the crystal dimensions when I measure the crystal on the software. So first I'm going to center the crystal, and it's just like doing the spindle stage, except we don't have to worry about the axis of rotation. We just have to rely on the axis of rotation being correct, or being fixed to the center, which may not be the case, but I've dealt with this before and it works. So I'm just making sure that that window stays on top. You have to click it twice sometimes to make it work. So yeah, I just rotated 90 degrees on the phi axis. And I'm just going to translate it down. Actually, the best way of seeing how far out the crystal should be is when the axis of the goniometer is in this position. So that is sort of orthogonal to the camera direction, which is that black thing. So yeah, now I can make sure that it's, about halfway out, so that the middle of the crystal is roughly in the crosshair. Just do a quick adjustment, spin phi, translate that down on the goniometer. And then another useful view is to just spin it over to the where the goniometer is right under the camera. So that is the center command. So that will bring the crystal around so that the phi axis is rotating and is just right under the camera. And you can check to see how far off the omega angle is rotating around the axis. But it's not going to be perfect. This is an old instrument. These things kind of vary a little bit over time, but this is pretty solid. Good enough. It doesn't have to be exact, but this is looking pretty good. That's good. And yeah, I'll just go back to the mount position. I'm going to close these leaded glass covers. And turn that light off. Alright, so back to the program. I'm going to close this. Go back to screen crystal. I'm going to take a frame, a short frame, just a still. And because this is a big crystal, I'll just go for 5 seconds. And this is a pretty old X-ray tube. So I'm not going to get the same type of signal I would with a new tube and a brand new detector. So for this size, I think this is a fair start of 5 seconds. If this was like a newer setup, I'm sure that would be like a 1 second exposure would be the same thing as a 5 on this. I'm just going to turn the lights out just for the camera effect here. And what it'll do when you click drive and scan here, it'll go to the position, which since this is a still frame, it's not going to move. And it'll ramp up the generator on the diffractometer to its operating voltage and current and give you a frame right there. So, and I change the scale so that goes from 0 to about 1,000 counts for this bracket, and you could see that these bright spots are diffracted beam. And the size of those looks about right, so I'd want to use an exposure that's pretty similar to this one in the future. I'm going to collect the determined unit cell and collect a data set. So I'm going to go back to about, we'll go to 4 seconds, just a little bit lower, and a 1/2 degree image width, and just click collect. And this will collect 12 frames in 3 runs, so a total of 36. And at that exposure, this might take like 5-10 minutes. It's just a starting point. You don't even really need to do this, but I'm going to be calculating a strategy for collecting a full data set. So I'm going to use this information. What this also does is it helps to figure out what exposure you should be using by seeing what the maximum intensities are on these spots. Okay, so once that's done, I'm going to go down and harvest the spots. And I'll click index. You could also go to reciprocal lattice at this stage too, but I'm going to go ahead and index and see what lattice setting this finds on here. So I found a good one right off the bat, because those calculated positions are matching our data set pretty well. I'm going to click refine once, and that looks pretty good. I'll click accept, go to the Bravi lattice, and it gives us a good field of merit for the orthorhombic face-centered lattice and a good score for the monoclinic C lattice setting. So interesting. We'll click accept on this orthorhombic one. It doesn't have to be totally correct at this stage, because my full data collection is going to be a full sphere of data, which means it's going to cover all angles of reciprocal space. So I'm going to view the reciprocal lattice now just to see what our data looks like. So here it is in 3 dimensions, and of course it's missing a lot because it was just for the unit cell collection. But there's a zone axis. There's a zone axis. And yeah, these are looking pretty good. So this is a reasonable crystal to collect a full data set on, I'd say, even if it's a little bit large. Now that we have a cell, though, we can index the crystal faces, but we'll need to acquire a video of the crystal with our camera software. And I save my frames to an external hard drive on here. That's how I have it set up. But if you're going to do this, you have to save it directly to the computer, I've found. So be aware of that. So I'm just going to save this to the computer. See, I have a whole list of ones I've done in the past. And then I'll transfer that to the external hard drive later. Because I like to do the refinement and the later stages of the process on a different computer, a much faster computer. I have to use this slow computer to run the instrument because it's the only one that will interface with the instrument, because the clock speed of the CPU has to be a specific range to interface with an Apex 1 detector, because it's just so old. Alright, here it is collecting images as it's rotating around the phi axis. Alright, so that's done. So I can close out of this and take a look, turn the light off again. I had the light on so that it could collect good images. I'm going to turn everything off. No sense in wasting power here. Close this, and I'm going to index some faces on here just to get good crystal dimensions. You don't have to do this now, you can do this later, but just for fun we'll do this. So that dashed line that it's showing up is the pole to a set of planes. So that plane, for example, and possibly one down here. Just like with the spindle stage, I'm rotating it so that the plane, so that the pole to the plane is in the plane of view. So click there, rotating until a pole comes into the plane of view. So theoretically there's one there. On the edges of the crystal. And this is a great way of measuring the dimensions of the crystal and just getting a general idea of where the planes are. So there's one right there. That's an obvious one. That's the same one that I indexed on the optical on the spindle stage. I just have to trim this up a little bit. The edge there. And when you're done with all this, you can click Remove Invisible Faces. And then OK. And alright. I will now see that those are now entered in. Those are the dimensions of the crystal. Like I said, it's a bit long of a crystal, over 700 microns. Or around 700 microns. Probably half that would have been better. But I'm going to calculate strategy now. And because this is such a slow computer, it's going to take forever, but I always collect triclinic scans. That means it's collecting a full sphere of data. And the reason is I don't mind having redundancy among symmetry equivalent spots, and it allows me to assess what the actual structure is a little better. It just makes the statistics a little bit easier, but it takes much longer. So what people do sometimes is that they'll just scan one crystal system or Bravais lattice symmetry above what they think the lattice is, so like a little bit, or I should say below, a bit lower of a symmetry than what they think it is. So if it was orthorhombic, you'd scan it as a monoclinic crystal so that it would collect a little bit more redundancy, just in case they didn't have the space group right or the lattice right. And that'll make them much shorter scans, but what I'm looking for is just full data set. I got time. Usually these end up being overnight scans anyway. you know, this one probably will end up being around that 16 hours. I'm going to select scan parameters after it figured out the okay, so I always just do a frame angle of 0.5 degrees, and then the exposure, yeah, 4 seconds was really good for that unit cell, so I'll use that same one. And it's just going to recalculate. So it's going to scan across at a half degree increments here, and this takes this computer forever, but of course I trimmed this out. It takes like 20 minutes. And then what you do is you go to the run experiment section, which is what this is. So that was calculate strategy, where we were. Yeah. And it calculated our strategy. Then you go to run experiments and then append strategy on the left here. And that'll bring in this table of what the diffractometer is going to do, where it's going to scan and how long, of course. You click validate to make sure the operations are valid, so it's not going to collide with some limit that's set on it. And then you click execute. Now, you can have predetermined tables also. I don't know where those are stored on this computer, but there are just scan routines that you can enter in or create your own if you want on that same run experiment window. But yeah, I'm just going back and checking these spots just to see where the counts are. So this is a bit higher counts, but that's okay. 10,000, it's pretty high, but that's fine. It's not totally overexposed. So, but remember, you got to change the scale on these. This is 100,000 or so. Or what is that? Anyhow, you could take a look at what the counts are on these spots and make a determination of what exposure you really need on these are. But I'm fine with that. It's not going to burn the detector to oblivion, so I'll just click execute.